Hello everyone, we are from group 3 and we will explaining Euclidean vector space. My name is Muhammad Naufal Ramadhanu.
My name is Muhammad Awar Ramadan.
My name is Gian Arkana.
My name is Fabian Putraswara.
And my name is Sakarayu Putri Nugroho.
And we will first start from introduction. What is Euclidean vector space? So, Euclidean vector spaces are fundamental to understanding geometry, physics, and computer science. They extend the idea of 2D and 3-dimension geometry to higher dimensions, where vectors can represent anything from forces to data points. And Euclidean vector spaces is a finite-dimensional space over the real numbers, equipped with an inner product that allows for measurement of angles and length. Next.
So, the topic that we choose is from driving direction and distance. Vectors are very useful in everyday life because they show both distance and direction. For example, when going on a road trip, knowing only the number of miles traveled is not enough. You also need to know which way to go. This is where vectors come in. And each part of the journey can be represented as a vector, combining the magnitude and the direction by breaking a trip into vectors. It becomes easier to visualize the route and make better navigation choice. In simple terms, vector turn ordinary driving direction into a clear picture of movement, showing not just the distance between cities but also the exact path to take. This highlight how vectors are not only a math concept but also a practical tool in daily life. And why we choose the orthonormal basis name is because the ortho basis is the foundation of simplicity and structure in Euclidean vector space. Just like an orthonormal basis makes computation easier, like dot products, projection, and something like that. We aim to bring clarity, precision, and orthogonality of ideas to mathematical discussion.
So for the next one is equation of Euclidean vector space. So the basic formula is usually phi equal u, comma phi, comma w, and blank blank blank, and the result is mostly r. And then for the other formula, like closure under factor addition, this is like if you add two factors in it, like u plus phi, the result is also same r. And then next one is closure under scalar multiplication. If you multiply a factor by scalar, the result is still same, is r. And the next one is commutativity of addition. The formula is u plus phi equal phi plus u. And then associativity of addition is so this is like u plus phi plus w equal u plus phi plus w. So the next one is additive identity. There's exists a zero factor, so like u plus 0 equal u. And then next one is additive inverse. So in every factor u, there still have minus u. Like for the formula is about u plus minus u equals 0. So next one is associativity of scalar multiplication. For the formula is a times bu equal ab times u. And next one is scalar multiplication identity. So for the formula is 1 times u equal u. So multiplying a factor, if it multiply with 1, the answer is always same, like like the factor. And then next one is distributivity of scalars over vector addition. So the formula is A times U plus V equal AU plus AV. The last one is distributivity of factors of scalar addition. So the formula is A plus B times U equal AU plus BU.
Okay, so here we have an example problem of Euclidean vector space. We have first the vector named U with the first member is 1, the second member is 0, and vector V, which the first member is 0 and the second member is 1. Here, to find the dot product between the two vectors, we need to times multiply each of the places of the members. Example, for the first members of each vector is multiplied, then we add all of the multiplications together. So here we have the first member of vector u, which is 1. We multiply it with the first member of vector v, which is 0. Here we have it. And for the second members, we have from u, which is 0, and from v, which is 1. 1 times 0 is 0, and 0 times 1 is also 0, which means that the inner product or the dot product is 0. Here, to find the length of the vector, we need to the length of the vector is the square root of all of the members squared and added. Like here in the length of vector u, which is the first member is 1, we square that, and we added it with the second member that's squared 0. 1 squared is 1 plus 0 squared is 0. That means the length is the square root of 1, which is 1. For vector v, we have the same matter, which is the first member 0. We square it and add with the square root of the second member, which is 1. We square root both, so 0 plus 1. Then we have the length, which is the square root of 1, which is 1. Here, to calculate the curve, the gradient between both vectors, we need to divide the inner product or dot product, which is 0, divided by both of the lengths of the vectors, which is 1 times 1, in which we have 0. And the cosine of that, which means that the angle is 90 degrees. And here we have another example. This time the vector u has members 1 and 2, and vector v, the members of vector v are 3 and 4. As usual, for the inner product, we times all of the members of each vector according to their spaces. For example, the first members are multiplied, which is 1 from vector u and 3 from vector v, and then the second members, which is 2 from vector u and 4 from vector v. Now, after multiplying both, we get 3 and 8. Then we add them together to get the inner product of 11. Now, for the norms or for the length of the vector, as before, we need to the length is the square root of all of the members of the vectors square rooted and added. Here we have the norms of U, which has the first member 1 and the second member 2. We square root the first member, which is 1, and square the second member, which is 2. We get 1 plus 4, and added both, we get the norm of U, which is the square root of 5. For V, we do the same thing. The first is 3 squared plus 4 squared, which comes to 9 plus 16. 9 plus 16 is 25, and the square root of 25 is 5. So the norm of V is 5. And now to calculate the angle between vector U and vector V, the angle between both of them is the we need to find the cosine of the angle is the inner product divided by the norms of U and V multiplied. We before have the inner product of U and V, which is 11. We put it top here. And then for both of the norms, we put it down here. So it will be the cosine of the angle between vector U and V is 11 over 5 to the square root of 5, which means that approximately the angle between vector U and V, which we use the negative of the cosine to get 10.3 degrees.
Okay, in this hard example, we are given two vectors. The vector 1 is U, which is 1, 2, 3, and 4. The vector V is 4, 3, 2, 1. First, we calculate the inner product, also called the dot product of U and V. To do this, we multiply the corresponding components of two vectors and then add the results together. So we multiply 1 times 4 plus 2 times 3 plus 3 times 2 plus 4 times 1. That gives us 4 plus 6 plus 6 plus 4, which equals 20. Next, we calculate the magnitude, also called the norm, of each vector. The norm of vector U is the square root of the sum of the squares of its components. So we calculate 1 squared plus 2 squared plus 3 squared plus 4 squared. That is 1 plus 4 plus 9 plus 16, which equals 30. The square root of 30 is the magnitude of the vector U. The norm of vector V is found in the same way. And then we calculate 4 squared plus 3 squared plus 2 squared plus 1 squared. That's 16 plus 9 plus 4 plus 1, which also equals 30. Taking the square root gives us the square root of 30 as the magnitude of vector V. And then now we find the angle between the two vectors. We use the formula where the cosine of the angle is equal the inner product divided by product of the magnitudes. That means we take 20 divided by square root of 30 times the square root of 30. This simplifies to 20 divided by 30, which equals 2/3. Taking the inverse of cosine of 2/3 gives us the angle. The result is approximately 48.2 degrees. Finally, we check whether the two vectors are orthogonal. Two vectors are also orthogonal if their inner products equal 0. Since the inner product here is 20 and the 20 is not equal to the 0, the two vectors are not orthogonal.
Okay, so that wraps up our presentation of Euclidean vector space. We, as group orthobasis, finishes ours. That's all. Thank you for listening.